This is an extended exam-style question which has been scaffolded into 6 sections. The first part asks you to show that f of x has one turning point and one point of inflection. You know that at a turning point, the first derivative of a function is equal to 0, and that for a point of inflection, the second derivative of a function is equal to 0. A. You start by finding the first and second derivatives of f of x. The product rule and chain rule are used. F of x equals 3x multiplied by e to the negative x implies f prime of x equals negative 3x multiplied by e to the negative x plus 3e to the negative x, which simplifies to 3e to the negative x multiplied by 1 minus x. Similarly, f double prime of x equals negative 3e to the negative x minus 3 multiplied by 1 minus x multiplied by e to the negative x equals 3xe to the negative x minus 6e to the negative x equals 3e to the negative x multiplied by x minus 2. Equating the first derivative to 0 gives f prime of x equals 0 implies 3e to the negative x multiplied by 1 minus x equals 0, which implies x equals 1, since 3e to the negative x is not 0 for any value of x. Turning point at x equals 1. Equating the second derivative to 0 gives f double prime of x equals 0 implies 3e to the negative x multiplied by x minus 2 equals 0 implies x equals 2. Since f prime 2 is not equal to 0 and f double prime x equals 0, the function changes concavity and there is a point of inflection at x equals 2. With this working, you have shown that there is one turning point and one point of inflection. B. To find the position of the turning point, we need to find f of 1 equals 3e to the negative 1 equals 3 divided by e. The coordinates of the turning point are 1, 3 divided by e. To identify the nature of the turning point, we can try the second derivative test. F double prime of 1 equals 3e to the negative 1 multiplied by 1 minus 2 equals negative 3 divided by e, which is less than 0. Since the second derivative is negative at the turning point, it indicates that there is a local maximum. C. At the point of inflection, x equals 2. F of 2 equals 6 multiplied by e to the negative 2 implies point of inflection at 2, 6 divided by e squared. Before we can sketch the graph, we need to find any intercepts. F of 0 equals 0, which means that the graph passes through the origin. The domain of the function is given as negative 3 less than or equal to x less than or equal to 3. To sketch a graph, you only need approximate values at the domain boundaries, so you can approximate e to 3 for an estimate. F of negative 3 equals negative 9e cubed is approximately equal to negative 243. F of 3 equals 9e to the negative 3 is approximately equal to 1/3. Now that we have all the information, we can sketch the graph. D. The gradient of the tangent at x equals 2 equals f prime of 2 equals 3e to the negative 2 times 1 minus 2 equals negative 3 over e squared. This means that the equation of the tangent is y equals negative 3 divided by e squared x plus c. Since we know the coordinates of the point of inflection, we can substitute for x and y to obtain a value for c. 6 divided by e squared equals negative 3 divided by e squared multiplied by 2 plus c implies c equals 12 divided by e squared. Therefore, the equation of the tangent is y equals negative 3 divided by e squared x plus 12 divided by e squared. E. At the x-axis, we know that y equals 0. 0 equals negative 3 divided by e squared multiplied by x plus 12 divided by e squared implies 3 divided by e squared multiplied by x equals 12 divided by e squared implies x equals 12 divided by e squared multiplied by e squared divided by 3 equals 4. F. With this information, you can sketch the required triangle and calculate the area of triangle ADE. The required area of triangle ADE equals a half multiplied by 4 multiplied by 12 divided by e squared equals 24 divided by e squared.